Hello everyone, and welcome to another Carsey Quick Bite tutorial. In this tutorial, I'll be showing you how to use the Slurm High Performance Computing Scheduler. Slurm is used to manage submission of jobs and to make sure that everyone gets fair access to the hardware provided through our High Performance Computing Center. Slurm stands for the Simple Linux Utility for Resource Management. But really, the developers were just Futurama fans, and so it's named after the drink in that show. As always, the first thing we're going to do is log into one of our clusters. Slurm, by the way, is used in many different locations, so what I'm going to show you has some things that are specific to Carsey, but any high-performance computing center that uses Slurm, these tools will be very, very similar. All right, so I'm on a Windows machine right now. I'm going to open up PowerShell so I can get to SSH and log into one of our clusters. It'll be a similar process whether you're in Linux or Mac. All right, I'm going to SSH into Hopper. I've set up my SSH environment so I don't need to type out my username and the whole path. I'm using key authentication so I can just enter in the password for that key and log straight into the Hopper cluster. Now, the first command I'm going to show you is qgrok, and qgrok is actually a homegrown program. It runs a lot of Slurm commands just to give an overview of the status of the cluster. So, qgrok, and it will print out line by line information about each Slurm partition. So, if you've seen the Torque PBS tutorials, you'll know that we organize compute nodes into partitions or queues. Those queues and partitions can have different properties, different limits on how long you can run jobs there, how many CPUs, how many GPUs are in those partitions. So right now, we've got a number of different partitions. Each one of these rows is a partition in Slurm. And it tells you basic information like how many jobs are currently running on each of those partitions, how many compute nodes are free, how many are busy, how many are down for maintenance, the total number of nodes. And then we've also added some more fine-grained detail that shows you how many CPUs are there total in those partitions, how many are available, how many GPUs, how many free GPUs, etc. And then over here on this side of the table, you can see the limits for the partitions. So General, for example, has a 48-hour job submission limit. And you're limited to 128 CPUs at a time and 372 gigabytes of RAM. Our debug partition is limited to 25 gigabytes of RAM, 8 CPUs, and 4 hours. We set up our debug partition like this so that it's unattractive to people who are running production jobs. This debug partition is intended for interactive jobs where you need immediate access to a node, and for debugging where you want to be able to see whether your code runs at all quickly. Once you're happy that your code is running, then you would move your job onto a production queue such as General, or if you've bought into the condo and you have access to one of these private partitions, you could run your software there. The idea is that because it has a 4-hour limit and only 8 CPUs, people who are running serious jobs will not be tying up this partition. As you can see, it has a node free. There's almost always a node free on the debug partition. And then once people are happy with what they've got and they're running on the general partition, they can run for up to 48 hours with a lot more resources. We're going to be using the debug partition for most of this tutorial because it has some resources free by design. The other partition that I'll talk about right away is this condo partition. So at Carsey and other high-performance computing centers, we're always trying to balance access to resources and fully using those resources, right? So we're always trying to balance how quickly can you get a job running versus making sure that no resources are being wasted. And that's a trade-off because the easiest way to make sure that you can run a job immediately is to have nodes always idle and available. But if nodes are always idle and available, they're being wasted if no one runs a job. So this condo partition, which you will see if you are part of one of these private partitions, is a special partition that scavenges resources that are idle from these other partitions. Okay, so for example, in the case of GeoDef, a research group purchased, let's say they purchased 4 nodes that they have access to, and when they submit jobs there, their jobs will always start immediately on those nodes. But if those nodes are not being used, then anybody else who has access to any of the other condo partitions can also run on the nodes in the GeoDef partition. So let's say that GeoDef has 1 node free, which it does right now. That means that if you submit a job to the condo partition, you can use that job. You can use that node, rather. That's great. That means you get to use someone else's resources sort of for free. The downside is if anybody in the GeoDef partition submits a job to GeoDef, your job will get kicked out of off that free node so they can use the node they paid for. And in that way, we try and balance making sure there's not a lot of idle hardware, but the people who purchased access to hardware can get immediate access to that hardware. All right, so that's the condo partition. The general and debug partitions were purchased by the Office for the Vice President for Research, and they are available to anybody at the university with equal priority. So one of the things we like about Slurm is that it runs something called the fair share algorithm that makes sure that no one has to wait too long in the queue before their job starts. And I'll get more into that later. The main difference between a high-performance compute cluster and a regular PC that you might be running in your lab or at home or your laptop is the scheduler. So the scheduler is what runs your software, allocates it to one of the dozens or hundreds of nodes that are available to run your hardware, your software. And so familiarity with dealing with this Slurm scheduler is really important. It's how you interface with the cluster. You can't just run any program you want like you would on your own machine and have it try to run immediately. It has to be scheduled onto a compute node to run there so you can get your results back later. So we'll spend quite a bit of time looking at Slurm commands that get the status of the scheduler, that allow you to interact with the scheduler to submit your jobs, etc. All right, so let's take a look at a few basic Slurm commands. They generally start with an S, and we're going to start off with sinfo. And I'm going to specify the partition that I want to get information about. So sinfo partition debug. And that's going to tell me things like how long can I run my jobs for, how many nodes are idle, ready to run jobs, how many nodes are, in this case, in a mixed state, meaning some of the CPUs are being used but not all, whether the partition is up or down for maintenance, and the name of the compute nodes that are in that partition. So in our case, compute nodes will always begin with the name of the cluster. So I'm logged into the Hopper cluster right now, and end with a number that identifies which compute node that is. All right. So you can see a lot of this information is repeated with qgrok. Qgrok is just behind the scenes formatting and running commands like sinfo and formatting it in a table for you. High-performance computing is all about allocating your software, your computations that you want to run, to appropriate hardware. So to start off with, we're going to pick out an example program that is very simple, just to get a sense of how this works. You can run any program basically with the commands I'm going to show you, but we're going to start off by just running the hostname program. All the hostname program does is return the name of the machine that it's running on. So it returns the name Hopper because we're on the head node of the Hopper cluster, and the head node always has the same name as the cluster. In all tutorials, we can only scratch the surface of these commands. Slurm is very powerful, very flexible, and it has a lot of options that we won't have time to go into today. So I want to take a quick moment to show you the man command. That stands for manual. So for example, we can say man hostname and get a lot of information, more information than you ever wanted to know about this simple program that prints out the name of the machine it's running on. And we can do that for all the Slurm commands you're going to see in this tutorial if you want to get more information about them. Man is implemented for almost all commands in Linux, and just to demonstrate that, you can even ask for the manual page for manual itself, and it'll tell you all about how to run this manual and the different kinds of manuals that are available. So let's use the manual command to find out more about this sinfo command that we already used. So we'll just type man sinfo, and it tells us all the different options that are available for this command for formatting the output to get different kinds of information about the status of the partition. Even though there are all these different options for sinfo, the commands I'm going to show you will cover 95% of what you need to do to manage your jobs. Even though there's all these other things going on, you won't need much more than I'm showing you. So don't feel overwhelmed by all the options that there are in these Slurm commands. Well, the first option I see here in man is -a or --all, and that just gives me information about all the partitions. Let's go ahead and take a look at that. I like to spell out the arguments I give to commands. It helps me remember what they do, but you can always use the shortcut, which will have one dash and then the first letter usually of the command. So sinfo --all shows me the status and the names of all the compute nodes on Hopper. And you can see a number of them have been allocated. That means the whole compute node is being used. All the CPUs on this compute node are being used. Some of them are using just some of the CPUs, and then some of them are entirely idle, waiting for software to run. All right, so let's try actually running a program on one of the compute nodes. To do that, we're going to use the command srun, so slurm run, and we're going to run on the debug partition because there's some idle resources there, so we can run immediately. And the program we're going to run is hostname. But again, this could be any program that you can run on the command line. It could be passed into srun and will be run on a compute node. All right, so what this command does is it talks to the Slurm scheduler. It says, I want to run the program hostname on the partition debug. I don't care what compute node in the debug partition it runs on. Anyone is fine. So we're not going to specify anything like that. And you're going to get some output. A lot of this output are just warnings and boilerplate information. So for example, it tells you that we haven't asked for any graphical processing units. That's fine. We don't actually have any graphical processing units on debug, so we can ignore that. It tells us what account we're using, what Slurm account. That actually has to do with the project that you're a member of at Carsey. It gives us a job ID, so it tells us a unique number that allows us to identify our job later. And then at the very end, it has the output of the command we ran. So we ran the hostname command, and notice that it didn't print out Hopper, it printed out Hopper 011 because it ran on the debug partition node Hopper 011. So it could just as easily have run on 012, but there was room on Hopper 11, so it ran there. We don't really mind which compute node it runs on. For most partitions, they are going to be identical. In this tutorial, I'm going to show you most of the commands that I use on a daily basis when I'm running jobs on Carsey clusters. So I just showed you how to run a very simple program. We also want to keep track of how our programs are doing, the status of the queue and what programs are running there. Usually because we want to see whether our program has started yet, has our program crashed, what's the status of our particular program. If we run squ eue, it shows us the status of all of the nodes. And here is the header that explains what each of these columns do. So the first thing it's going to show you is the job ID. So that's the unique identifier that was assigned to your particular job. And job is just a term here that means a program running on a node. It tells us what partition this is running on. So in this case, stran is running Trinity on the bugs partition, and it's been running for 22 hours. It's running on Hopper 013, and it has job ID 3656714. By the way, these numbers are sequential. Hopper's been up for a couple of years now, and we've run, it looks like, 3.6 million jobs over those past couple of years. So these clusters do get a lot of use. All right. When people run this command, sometimes they worry because they'll see a large number of jobs. So here, for example, are a lot of jobs queued up on the pathogen queue, pathogen partition, and you might worry that with all these jobs queued up, how is my job ever going to run? It's important to look at the status of the jobs. So I mentioned the fair share algorithm, and the fair share algorithm will make sure that everyone gets to run their software in a reasonable amount of time. So even though this user has lots and lots and lots of jobs queued up, these are not jobs that are actually running. In this case, they're being held for priority because there's a maximum amount of resources that any one user can have at a time. And there are other things that are going on, like if you've used the cluster heavily, you get less and less priority so that someone who's coming along and hasn't used the cluster in a while gets to run before you do. The idea there is just that if someone is running continual jobs, they don't get to monopolize the cluster, whereas people who are running more infrequently get to run in a timely manner. All right. You can see here that these jobs have the PD status. That stands for pending. That means they are not running yet. But this user does have 1, 2, 3, 4, 5, 6, 7, has 8 jobs running in the running status. So they're using their Hopper 17 compute node. And notice that each of these jobs is not taking up a whole node. It's just taking up a few CPUs on this node, so they can have 8 jobs running on the same compute node. So even if you see someone with a lot of jobs running, in this case, they're only using 1 CPU out of the 32 available on that compute node. All right. So let's take a look at just the jobs that are currently running. We can do that with -type R. Oops. Let me change that to -tr. And now we're only seeing the jobs that are actually in the running state. And you can see there are a lot fewer jobs in the running state than there are, for example, in the pending state. Let's go ahead and look at a list of all the jobs that are running on the whole Hopper cluster. Let's see how many that is. I'm going to pipe this into a little command called word count. I'm going to count the lines. So there's 192 different jobs running currently on the Hopper cluster. All right, so let's start learning how to allocate resources to software. The way we're going to do that with our srun command, and again, we're going to run on the debug partition, is with command line arguments like end tasks. So at a simple level, all high-performance computing, all parallel computing is just running lots of copies of the same program or similar programs to process data. All right, so if we want to analyze 100 images instead of 1 image, we run 100 copies of our program with 1 image per copy of the program, and that way we can do a lot more work with a lot more hardware. So we want to allocate software, copies of software, to CPUs at least. And we're going to also allocate memory and other things. But at the very basic level, we're allocating copies of programs to CPUs. So this ntasks argument says to Slurm how many copies of the program to start. So let's go ahead and use our hostname example again. Oops. All right. And we're going to say start up 2 copies of hostname and run those on the debug partition. By default, each copy of a program will get 1 CPU. So I know there are plenty of CPUs available on the debug partition. It'll start 2 copies of hostname, they'll run on 2 separate CPUs, and we'll get the results out immediately for both programs. We don't have to wait for one to finish and the other to start. All right, so we ran 2 copies of hostname. We got the same warning information as before. We got a new job ID running on Hopper 11, and we got 2 outputs. We got 1 output for each copy of hostname. Now, so far, of course, this is going to be a little bit ridiculous that we're running hostname on a supercomputer, but by the end of the tutorial, we'll be running some more interesting software that actually cares about more resources and is able to use those resources to solve bigger problems faster. So we will get there. And we can set this number to be whatever we like. So I'm going to ask for 8 copies of hostname to run on the debug partition. Here are our 8 outputs. And again, they're all running on the same compute node because it has plenty of CPUs and can run 8 copies of hostname on that compute node. All right, so we just allocated 1 CPU per copy of our program. That's what happens by default. But lots of software is able to use more than 1 CPU at a time. So most mature software, most well-developed software, automatically takes advantage of multiple CPUs. That's what's driven the increase in speed in large part for even your cell phones and your laptops and your desktops, is just adding more and more CPUs. And so software has been developed to take advantage of those multiple CPUs to speed things up. All right, so how do we tell srun, Slurm, to allocate more than 1 CPU to each copy of the program we're running? Well, we can do it like this. So we're going to say srun partition debug, just like before. We're going to say, in this case, 4 tasks. So we're going to run 4 copies of our program. And we're going to say CPUs per task is 2. And then we're going to run hostname again. All right, so 4 copies of our program, 2 CPUs allocated to each copy of the program, and the program that we're running is hostname. And you can see we get 4 outputs because there were 4 copies of the program. We don't get 8 outputs because hostname is a very simple program. It doesn't know how to use more than 1 CPU at a time. So the point I'm trying to make here is that you can ask Slurm to allocate hardware to your programs, but it has no idea whether your programs can actually make use of that hardware. That's up to you. That's up to you as the person running the software, developing the software, to know whether your programs can actually use more than 1 CPU at a time. A program that just prints out the host name of the machine it ran on is not likely to be able to use or want to use more than 1 CPU. But we will get to software later in the tutorial that definitely uses more than 1 CPU and even more than 1 compute node at a time. We're going to keep on building up the sophistication of this srun command. It's going to get long and it's going to get frustrating, but then I'll show you some ways of making it so you can save all these settings in a script, and we'll run it that way. We can also tell the Slurm scheduler to give us more than 1 compute node on which to run our programs. So far, everything we've done has run on one compute node. But sometimes if you want to balance a computation across more than one computer, you might want to allocate more than one computer explicitly. Perhaps you have a lot of memory that you want to use, more than CPUs, and so you want to spread the computation across lots of computers that have lots of memory. So we can do that by entering srun again. And this time we're going to say nodes, in this case 2. We're going to ask for 2 compute nodes. And then we're going to say n tasks per node. Let's run 2 copies of our program on the 2 nodes. And we're going to run hostname again. And notice that we got 4 outputs because we ran 4 copies of the program, right? So we have 2 copies per node and 2 nodes, so 4 copies of the program ran. And notice that the output, for the first time, we actually ran on Hopper 12 because we enforced that we were going to have 2 compute nodes to run our programs on. So one of them ran on Hopper 11, or 2 of them ran on Hopper 11, and 2 of them ran on Hopper 12. And of course, we can combine all these things together. So now I'm going to say CPUs per task 2. Notice that we get 4 outputs, again on Hopper 12 and Hopper 11. And this time, we allocated a total of 8 CPUs. So we had 2 copies of the program here, 2 copies here for a total of 4. And then we have 2 CPUs per program or per task. So we have 8 CPUs allocated altogether and 4 outputs for the 4 copies of the program. All right. So one of the reasons that people use high-performance computing clusters is that we have lots and lots of CPUs, right? We're going to let you use hundreds of CPUs at a time to get your research done that much faster. The other thing that we provide, the other resource that really matters, is memory, is RAM. So we can access memory. We can specify how much memory to use with the --mem command. In this case, I'm going to say --mem 4 GB. And that will allocate 4 gigabytes of RAM to each node. So here, I'm going to have a total of 8 gigs of RAM because there are 2 nodes. It's not a function of the number of CPUs or the number of copies of the program. This --mem applies to the nodes themselves, that node level memory allocation. If you don't specify this, you get a default allocation. That default allocation will be the total amount of memory on the node. So most of our nodes have 96 gigabytes of RAM on Hopper, divided by the number of CPUs. That's a calculation I don't want to make. So I like to just specify exactly how much RAM to allocate for my program. And just like knowing whether the program is capable of using multiple CPUs, I have to know how much RAM, how much memory does my program need, and the instance of the problem that I'm passing to my program. How much RAM does that need to process that calculation? If you exceed this memory allocation, your job gets killed. So this is a little bit like a contract. You're saying, Slurm, give me a certain amount of computational resources in terms of CPUs, and give me some RAM, and I promise I won't use more than that. If I do use more than that, Slurm is going to kill your job and return the resources back to the pool for other people to use. The reason it does that is that if a program ends up using more RAM than it's supposed to, it can actually cause the compute node to crash. So make sure that when you allocate your memory that you're allocating more RAM than you really need. And I'll show you some tools later on to determine how much RAM you need after you've done your initial program runs. All right, so why does all this matter? Why am I showing you all this? High Performance Computing Center provides you more hardware than you'll have back in your lab, and you have programs, calculations that you want to run. The scheduler is the intermediary that takes your programs, allocates them to the hardware we have, and gives you your results. But the scheduler doesn't know anything about your software. It doesn't know if it's capable of using more than one CPU per copy of the program. It doesn't know whether you can use multiple compute nodes at a time with your software. It doesn't know how much RAM you need. These are all things that you are telling Slurm to give you, and it's assuming that you are asking for appropriate resources. So sometimes, more and more rarely, but sometimes we'll see people who've allocated hundreds of CPUs, 400 CPUs at a time, for example, and then when we look at their resource utilization, they're only using one CPU out of those 400 because the program they're running doesn't know how to use more than one CPU. So that's the purpose of Slurm, and the purpose of this tutorial is to show you how to allocate the appropriate resources for your particular software and your particular problem. So that means that there are 4 questions to ask yourself before you start running your software. 1, can it use multiple CPUs? 2, can it use multiple compute nodes? That involves the program using the network to talk across compute nodes. How much RAM does it need to use? And finally, more and more often, can it use GPUs? So these GPU accelerators have made lots of software run much, much faster, but that software has to be written to take advantage of GPUs. All right, so this command is already getting pretty long. I don't want to have to type this in every time we want to run our program. Slurm has a couple of mechanisms for reducing that amount of typing. The first one we'll look at is something called salloc. This command is getting increasingly long and unwieldy. I don't want to have to type this every time I want to run hostname. So what we can do instead is pre-allocate our resources. We simply replace srun with salloc, and we take away the program that we're going to run because we're not going to run any programs right now. We're simply going to ask for the resources from Slurm, and then every subsequent time we use the srun command, we don't need to give any arguments. It'll just use whatever we gave salloc. All right, so Slurm allocated those resources for us. We've got 2 nodes now, and now I can simply say srun hostname, and I get the output without having to redo any of those arguments. And I can do that as many times as I like. So let's change this to a different command. This time I ran uptime, which just gives me information about how busy a node is, how long it's been up, how many users are on it, for example. So now I can just rerun srun and run as many programs as I want without having to reallocate over and over with that long command line for srun. Once I'm done with my allocation, I type exit to relinquish those hardware resources back to the system so that other people can use them. And then I can allocate a different amount of resources if I like. So here I'm just going to allocate 2 nodes, and by default you get 1 CPU per node. So this will be just 2 CPUs on 2 nodes and 4 gigs of RAM. And now I can do srun hostname again. And this time I only get 2 outputs because there were only 2 copies of the program, 1 per node, with 1 CPU each. And I'll relinquish that again. Everything I've shown you so far has been interactive. What that means is I start a program, I type some information, and I get the results of that program written to my screen right away in real time. I want to emphasize that is not how most high-performance computing is run. Most of it is done in batch mode. So far, everything's been interactive mode. just like you were running it on the command line on your own computer. Now, one of the downsides of that is that if there weren't resources available when I ran salloc or srun, I would have to sit here waiting for them to become available. It doesn't normally take very long at Corsi, but it might be an hour. And I don't want to be sitting here waiting to type my command or see my output for an hour in front of the screen. And that kind of defeats the whole purpose of an HPC center, which is that you send your jobs off to the scheduler, it finds the appropriate hardware for you, runs the programs, gets your results, saves them for you, and then you can come back and review the results. So one of my favorite things about high-performance computing is that I can just set up my scripts, my machine learning, computational chemistry, whatever it is, have it do the analysis, which usually takes a long time, right? These are large problems, so it might take hours or days to do the analysis. And then I get an email saying that my results are ready. So I can be doing something else. I'm not tying up my laptop or my PC, running computations. That's all happening at the High Performance Computing Center. I can use my workstation for what it was intended for, which is reading email, browsing the web, writing papers, etc. All right, so how are batch jobs handled? It's a little bit like salloc, except we're going to actually write a bash script. So this script is going to contain the commands that I want Slurm to run on the hardware that it allocates. So the rest of the time here, we're going to be looking at primarily batch jobs, not interactive jobs. And occasionally we'll run an interactive job for debugging, because it is useful sometimes to get immediate output if you're not sure whether a program is going to run yet, or you want to understand how the syntax works. So we'll look at a mix of interactive and batch jobs going forwards. Since we're going to be working with text files from now on in the tutorial for these Slurm scripts and bash scripts that we're going to be using, rather than having to type those all out, I'm going to give you a Git repository from where you can download these scripts. So to do that, we're going to enter git clone. So we downloaded a number of files. If I go into this workshops directory now that we've downloaded and type tree, you can see an outline of the different scripts, some sample input data and programs for various applications. And the first thing we're going to do is take a look at an example Slurm script. We're going to do that with the cat command, which simply prints out text files. And the path is cat intro workshop slurm workshop example .sh. And that prints out the contents of this text file. So it ends in a .sh, just to remind us that it's actually a shell script. And a shell script can contain any commands that you could type in to the terminal here in bash. The first line tells the system that this is a bash script. These lines here that all start with #sbatch are directives to the Slurm scheduler, and they might look familiar to you. So here's partition debug and tasks 4. These are exactly the same arguments that you would have given to salloc or to srun. It's just that we can put them into a text file here and not have to type them out at all whenever we run this. There are a couple here you haven't seen yet. So --time, for example, tells the scheduler how long you want the hardware for. Now, this isn't telling the scheduler how long your program is going to run. This is telling the scheduler when can it take back the hardware. So if you say 5 minutes, as in this example, and your program runs for 5 minutes, 10 seconds, Slurm is going to take the hardware away from your program, killing your program at 5 minutes, and your program's not going to finish properly. So you always want to make sure that you allocate more time than you need for your program. It's also the case, though, that if you allocate a lot of time, the more time you allocate, the harder it's going to be for Slurm to schedule that time. It has to find when those resources are going to be available. So if you have a 5-minute program and you allocate or you ask for 48 hours, it's going to take a lot longer to find that time for you than if you just asked for 6 minutes. So that's a trade-off you have to be aware of. The more time you ask for, the more likely your program will finish, but the longer it's going to take for that program to start. Job name is simply free text that puts a label on your job. So when we ran SQ earlier and we saw a variety of labels on those jobs, that's how those labels were set with job name. And then mail user, this is where you can type in an email address to send notifications to. So when the scheduler starts your job, it can send you an email. If the job crashes for some reason, and when it ends, it can send you an email. And in this case, we're going to ask for all 3 of those. So we're going to ask for all 3 event types to be emailed to us: start, abort, and end. And then finally, after the Slurm directives, we have a command to run at the bottom of the script. All it does is run that hostname program that we've been running all along. It's just in the script. It's going to be run by Slurm on the resources we ask for. All right, so let's go ahead and try executing or submitting this job script. To do that, I'm first going to cd into the intro workshop directory, and I'm going to use the command sbatch. So for interactive jobs, we use srun. For batch jobs, we use sbatch. And I'm going to say sbatch slurm workshop example.sh. All right, so we've submitted a batch job. If all goes well, we get a job ID back, and we get a reminder about which account we're using. But that's the only output we get, because this is a batch job. It's not an interactive job. All of that text that would have been written to screen has nowhere to go. It gets saved to a file instead of going to screen. So if I take a look and I do an ls in my directory, I've got a new file here. Slurm dash and then a number, and notice that that number corresponds to the job ID that the job I just submitted. That file will contain everything that would have been written to screen if I had done this with srun. Let's take a look at the contents of that file. And you can see all it contains is Hopper 11, which was the output of hostname. Let's take a second just to go over exactly what's happening. So I've been throwing a lot of commands at you, but let's take a high-level look at the actual architecture. All right, so imagine we have the head node, right? In our case, that would be Hopper. And we have a couple of users who are logged into the system. I'm logged in. Many other people are logged in at the same time, all running different software. So user 1 might want to run program A. User 2 might want to run program B. And they've each written a batch script, script A and script B, that contains the commands to allocate resources with sbatch and to run the program B. And of course, on the back end, we have a bunch of compute nodes waiting to run. We submit our job with sbatch to the scheduler. And the scheduler is going to find the hardware that we requested in our script. So user 1 in their script A requested 3 compute nodes. User 2 in their script requested 2 compute nodes. Now Slurm, once it's allocated these resources, and remember it might take a little while to allocate the resources, is going to run script A on the first CPU of the first compute node allocated. Not on all of them, just on the first one. And then, in our script, we will find some way of running the program A or B on all of the CPUs that we were allocated on all of the nodes. All right, so that gives you an overview of kind of a schematic of how Slurm takes these scripts and programs, allocates them to compute nodes, and executes them. In order to explore that further, we're going to start looking at a different example. We're going to move on from hostname and take a look at a little Python program that calculates or estimates pi. And that's something that I've used as an example in other tutorials in this playlist. So I'll go over it just really briefly here. So our little pi calculator is going to rely on the fact that the area under the curve 4 over 1 plus x squared is equal to pi. And we can estimate that area by just looking at the Riemann sum of these rectangles. So we're going to find some number of rectangles where the area between the actual value of pi and our estimate is these little triangles that don't quite line up with the function 4 over 1 plus x squared. All right. Here is the Python program. It's under the code directory in the Git repo that you downloaded. It's a Python program. The first thing you'll see is it depends on NumPy. The reason for that is we want to compare our estimate of pi to the numerical value of pi stored in NumPy. Now, it's not, of course, that NumPy's value is perfect, but it gives us some point of reference to say how accurate is our calculation based on the number of rectangles we're using. We'll also print out how long it took to calculate pi. The difference between our estimate and the NumPy version, and the number of steps that were passed in. Now, this program is very short. The real heart of it is just this for loop that adds up the areas of the rectangles under that curve. So here's our 4 over 1 plus x squared. We're going to add those together and print out our value. Okay. All right, so the first thing we're going to have to do is quickly install this NumPy library so we have a reference value to compare to. And we can do that with Conda. That's a Python library manager. So we'll first load miniconda 3. And then we'll be able to type conda create. We're going to create an environment to install our NumPy library in. We give it a name. We're going to call it NumPy. And then after the name comes a list of the libraries that we're going to install. So in this case, we're just going to install one library, which is NumPy. It's going to go out to the internet, find this library and all its dependencies. It's going to download the code and then install it for us. When you're prompted, say yes to downloading not only NumPy, but all the dependencies that it found it needed. All right, great. So we've finished downloading and installing our NumPy libraries. We can access them with source activate NumPy. You can see our prompt changes. You can also use conda activate NumPy. You'll be prompted to initialize conda if you prefer that. I'm going to now interactively run our pi calculator just to make sure that we have a good idea of what the output is going to look like. So we're going to run srun partition debug as before. That's the point of the debug partition, is for testing out software like this interactively. Now, this program only knows how to use one CPU. It's in no way parallel. So we're just going to say one copy of the program on one CPU. That's what ntasks1 does. It's a Python program, so we're going to run Python and then give our code as an argument to that. And it's calcpy serialpy. And this software takes an argument, which is the number of rectangles. And so the point of this is we're going to vary the number of rectangles to play around with making this problem take longer, need more resources, and we'll find out how to allocate more CPUs to speed everything up. Let's start off with 10. All right, so we've interactively submitted our Python code with an argument of 10 rectangles. It's gone to the scheduler, and it's now looking for resources to run this program. All right, and you can see, again, because it's an interactive job, we got our results immediately on the screen. The difference is only 8/10,000ths between our estimate, even with only 10 rectangles, and the value reported by the NumPy library. Here's our value of pi that we estimated. It took something like 4 milliseconds to calculate those 10 rectangles. So now that we're confident that we sort of know how to run this, let's take a look at a batch script. I'm first going to unload this environment. It's sort of dangerous to leave conda environments loaded, especially if you're going to do batch job submissions, because then you run the risk of having conda environments loaded inside of other conda environments, which gets complicated and tends to break things. So I'm going to deactivate this environment before we move on. All right, so that's deactivated now. And let's take a look at a batch script that we wrote to do the same thing that we just did interactively. It's calcpy serial to sh. Here's our script. It's a bash script, so it has hashbang bing bash. And we have our sbatch directives, very similar to the ones we put on the interactive command line. We can add our email address here if we want to get notifications about that. And we've got a name, and we limited it to 5 minutes. And then everything else is just what we typed on the command line. So module load miniconda 3, we're going to source activate our NumPy environment. We're going to then run our code just like we did here as the last line of our batch script. But in this case, we're not going to run with 10 rectangles. We're going to run with 1 billion rectangles. And that is just so the program takes long enough for us to have a chance to take a look at it. Many times when you're running your own software, it's going to take hours or days to run, and you want to be able to take a look at the status. So let's submit that batch job. There it goes. We got a value back. Let's take a look at the status with squ-eue-me. That shows my jobs. I can see that it's currently pending. Hasn't started yet. I run it again, and now it's in the running state. I run this again, and the time is increasing. I can actually put the word watch before any command, and it'll rerun it every 2 seconds and sort of give us a live update of our job. So we're going to watch this until that line disappears, and that's how we know that our job is finished. Now, of course, normally if this was taking a very long time, you'd log out, you do whatever else you had to do, and wait for the email that says it's completed. All right, so it disappeared. The job is complete. And if I type ls, you can see I have a new output file here. Let's take a look at that. And it has exactly the kind of input that we had before, that we ran interactively, this time with 1 billion steps. Now the difference between our estimate and the actual value of pi reported by NumPy is infinitesimal, but it took about 80 seconds to run. So that's long enough for us to start thinking about how to make this even faster. So this is just serial, running on one CPU at a time. And in fact, I think I'll rerun this and show you that it really is running on just one CPU. So I resubmitted it. And I want to see, when it starts up, which node is it running on? Let's use watch to avoid typing this over and over. All right, there it goes. It's on Hopper 11 again. So what you can do is you can actually SSH into a compute node if you have a job running there. So let's run into Hopper 11. And I'm going to run a program called htop. htop is a nice program that gives you an overview of what's happening on a computer. So in this compute node, we can see here is our program, Python code calcpy serial pi with 1 billion rectangles. And it's using 100% of one CPU. So each of these bars corresponds to one of the 32 CPUs on this compute node. We can see how much memory is being used. In this case, 12 gigabytes out of 92. But because this is a serial program that only uses one CPU, we're only ever going to see it use one of these 32. Okay? So the next thing we're going to do is start learning how to use more than one CPU and really take advantage of what HPC centers can offer. Once I'm finished with HTOP, I'm going to press Q to exit. Notice I'm logged into this compute node. I'm going to type exit to get out of there. Let's see if the job is done yet. Yep, it's done. And I can show you another tool called SEFF that I can use to see how efficiently resources were used. So I'm going to put in the job ID, and it gives me useful information about how well I use my resources. So, for example, we used 12 megabytes out of the 3 gigabytes of RAM that we allocated. Which is just 0.5%. So we're allocating way too much memory, right? We don't need to allocate this much memory for that little tiny program. So we would scale back the amount of memory we ask for in the future. But the CPU efficiency is very high. 97.53% of our one CPU was utilized. That's really great. That means we're efficiently using the one CPU we asked for. So far in the tutorial, you've seen how to run programs interactively, how to run them in batch mode. But everything we've done so far has been using really just one CPU per program. The rest of the tutorial is going to start looking at how to use multiple CPUs at a time. The first thing we're going to look at is called an embarrassingly parallel problem. And this is where we map many copies of programs to many CPUs, kind of like we did at the very beginning with having multiple copies of hostname running. Only this time they'll be looking at something useful, like different input files. One of my favorite examples of CARSI being used efficiently is a psychologist here at UNM who wrote Python code to analyze brain images. And his Python code took about a day to run on his laptop or his desktop, and that's great. But now he wants to look at 300 human subjects. So now he's looking at almost a year of runtime to analyze his data set. Well, coming to CARSI, he was able to use 300 CPUs all at once, and now his runtime is back down to 1 day because he's able to divide that workload among those 300 CPUs. That is what's called an embarrassingly parallel problem. It's called that because it's almost embarrassing how easy it is to just give more and more hardware resources and speed up the amount of work you can do. This is Cleve Moeller. He was a math professor here at UNM and co-founder of MATLAB, and really a giant in the field of high-performance computing because he and his students were able to create efficient matrix algebra libraries that were able to underpin all sorts of different problems, from machine learning to computational chemistry and all sorts of other fields. So he coined this phrase, embarrassingly parallel, and it really means that if you double the number of CPUs, you can double the amount of work you can do. So if we have 1,000 inputs and 1,000 CPUs, we can calculate that in the same amount of time it takes for one CPU to calculate with one input. So let's take a look at that next. And then we'll move on to more difficult problems where we're going to use lots of copies of programs on lots of CPUs that are going to solve one problem rather than having a bunch of different problems, one for each program. The reason it's so efficient when you look at these embarrassingly parallel problems is there's no communication between the different problems, right? They're all working independently. They can just benefit from scaling up over CPUs. There's no collaboration needed between the programs to solve any of these problems. All right. We're going to use a mechanism that's built into Slurm called Slurm arrays. Slurm arrays are very basic and very clunky, but they can be very useful in a lot of cases. So let's imagine that we have our CalcPy simulator here, and we want to know what is the relationship between the number of rectangles and runtime and accuracy. We'd like, for our paper we're writing, right, we're going to submit to Nature on this amazing calculator, we'd like to know for many values what the outputs are like, for many values for the number of rectangles to include. So one way we could do that is we could just write hundreds of scripts, each of which had a different value for the number of rectangles to pass into CalcPy. And people sometimes do that. People sometimes write other scripts that generate a whole bunch of Slurm scripts that they submit. But Slurm has a mechanism built in that allows you to spawn a lot of jobs based on a single script. Okay, let's take a look at that. All right, so I've written this script for you called CalcPy array, and it looks very, very similar to the CalcPy serial. In fact, at the bottom here, it's actually going to run CalcPy serial. But notice that there's one extra line here, and that is dash dash array. Dash dash array, in this case, I've set it to 12, 1 through 12, will spawn 12 different jobs when you submit this single script. Each of those jobs will be identical except in one respect. The value of this variable, and in bash a $ followed by the name as a variable, the value of this variable called Slurm array task ID will take on one of these values between 1 and 12. So the first instance of the job will take on the value 1, the second will take on the value 2, all the way to the last instance, which will replace this variable with the value 12. That allows us to use this as a template to start up a whole bunch of jobs and just vary one variable between the jobs. And what we're going to do is, first of all, in the script, we're going to just echo out, for debugging purposes, the name of the machine we're running on and the value of this Slurm array task ID. Then we're going to do what we did interactively. We're going to module load miniconda 3. We're going to source activate our NumPy environment. And then we're going to calculate the number of steps to pass into our Python code. So this variable numSteps is going to take on whatever Slurm array task ID is. Remember, that's a value between 1 and 12. And we're just going to append some zeros. Okay, so this is just a quick way of doing a parameter sweep over 12 different values of inputs into this CalcPy program without having to write 12 different scripts. Okay. Let's go ahead and run that with sbatch as usual. It's submitted. We're going to run watch here to keep an eye on those 12 instances. And you can see how they've all been queued up automatically. Notice the command I ran was watch squeue -- -array -- -me. You can see them executing. These were waiting for the others to finish so they could execute. Because there were 8 CPUs available, we ran 12, so those 4 had to wait for the other 8 to finish. Control-C to exit. And now we have 12 new output files. So just like before, we've got slurm dash the job ID, but for arrays, we then have an underscore and then the array ID. So let's take a look at the output of slurm 3659941_1.out. It says calculating pi with 10,000. And look, there's where we printed out here with our echo, just prints to the file. We echoed the name it ran on, which is Hopper 11. And we echoed -1, which was the Slurm array task ID value, which translated into 10,000 steps because we added these 4 zeros. Let's take a look at the last one at 12. So, whoops, 12. So here is the value of Slurm array task ID 12. That translated into 120,000 steps. And let's see, it took about 10 times longer, which was what you'd expect with 12 times as many steps, for that to complete as it did for this instance with 10,000 steps to complete. Okay, so now we already have a straightforward mechanism for generating a whole bunch of jobs with different values with a single script. I'd like to run this again, but this time we're going to take a look with htop at what's going on. All right, so instead of adding 10,000, let's give a few more zeros here so we have enough time to actually see what's going on. Let's submit that job. We're waiting for it to start so we know what node to SSH into. There we go. It's on 11, so it's SSH into Hopper 11. We're on htop. On htop, I can see that we're now using several CPUs because we have these individual instances with different inputs running on this compute node. So some of these are probably running on, well, I guess you're running 8 at a time. So that's the maximum we can run right now. When these 8 are finished, the remaining 4 of the 12 total jobs we scheduled will start running. All right, I'm logged out of Hopper 11. I don't want to wait for this job to finish, so I'm going to cancel it with scancel, S-C-A-N-C-L-E-E-L, and say me, that's going to cancel all of my jobs. And now you can see I had no jobs running. All right. So that's an example of an embarrassingly parallel computation. We can take a look at the efficiency of our hardware usage, just like we did before. We just have to remember to reference the job ID with the underscore job array. All right, so we can just say SEFF, that was our job ID, underscore 1, for example. And again, we had 97% CPU usage. I mentioned that job arrays are a little bit clunky, and I think you saw how that can be. They do have a place. So for example, if you named all of your input images or all of your input data files for machine learning with a naming convention that allowed you to reference them by a sequential number, which would be the job ID, that's great. There's another program called GNU Parallel. It's been around for a very long time. It's extremely sophisticated, very, very useful, has all of the features you could imagine. I have another tutorial video that covers that in detail, so I'm not going to delve into that here, but I do want to show you that there's a reference file for GNU Parallel here in your Slurm directory. It's just called CalcPy Parallel. And here we run the parallel command, and it runs the same Python code. There's some mysterious syntax here, but it can do things like it can read specific values from an input file, which is really much nicer than having to play around with the array job IDs and adding values to them. So you can just specify a text file, read it in with GNU Parallel, and do much the same thing. It's not spawning multiple jobs, though. This is a single job, and it's doing this parallel computation within that single job. So depending on your use case, that might be more or less flexible than the array jobs from Slurm. All right, so now you know about interactive Slurm submissions, batch jobs, embarrassingly parallel batch jobs. Let's move on to the last part of the tutorial where we look at coupled problems. So a coupled problem is one where we need lots of copies of our programs running on lots of CPUs to collaboratively solve a problem. So this is not independently solving a bunch of different problems. This is collaboratively solving a single problem. Most research software, mature research software for HPC will use something called MPI, the message passing interface, because these copies of your program need to talk to each other to solve the problem. Okay? That's the fundamental difference between embarrassingly parallel, where there's no communication, and coupled problems where there has to be message passing in order to solve the problem. So MPI has been around for decades. It's by far the most widely used coupled problem library for communication, and it'll be built into whatever software you're running if it uses multiple, even multiple CPUs sometimes, but certainly multiple compute nodes. It's not that you need to know how to program this unless you're writing your own MPI code, but it's good to understand the frameworks needed to run your MPI code, because when you start it up, you're going to have to use something like srun or MPI run to tell it that it's an MPI program that can communicate with other copies of itself. All right, so let's take a look at an example of that. So the first thing I'm going to do is I'm going to show you a Python code that is a variation on the serial code you already saw. Let's first remind ourselves what it is we're doing here. So that pi estimator just sums up these rectangles. Now, if you were in a classroom, taking a calculus class or something, and you were allowed to break yourselves up into groups where you could solve this problem together, you might think of some ways where you could leverage the fact that there are several people working on the same problem. One way you could break this up is by assigning, if there are 4 of you, assigning one person to calculate one rectangle, the next person to calculate the next rectangle, and that way break up the problem across the 4 of you, so you could perhaps solve this in a quarter of the time. It wouldn't quite be a quarter of the time. So here's our example of assigning person 0 to calculate the first rectangle, and then going round robin style to calculate all of them. It wouldn't quite be perfectly 1/4 of the time, or in this case 1/3 of the time, because there are 3 people. Because at the end, someone has to take all these partial results, all these collections of calculations, and add them all up together to give a single value. And only one person is able to do that. You can't divide that final summation up among a bunch of people. Right? So it's not going to be quite 1 over the number of people time to solve this, but it's going to be pretty close. The other reason why it's not going to be necessarily exactly scalable the way we'd like is that there might not be, the number of rectangles we're calculating may not divide evenly by the number of people working on the problem. That's another reason why it won't always be perfectly 1 over the number of people working on it. So the analogy of students in a classroom dividing this problem up and working on it works exactly the same for an MPI program. So instead of students, we've just got copies of our program all working on a piece of the problem, and then one of those copies has the job of taking all the partial results and summing them together. All right, so that is just an example for this particular problem, how we might turn it into a coupled problem with communication to demonstrate how MPI is used. So let's take a look at the MPI version of our CalcPy problem. So we're just going to I'm going to use Emacs this time, so we got some syntax highlighting. So Emacs code, CalcPy, MPI. Oops. Looking at the Python version of this. It's a little bit longer, but not really that much longer than our serial version. Everything here in red are comments to help you understand the code, but basically we have the same for loop we had before, but now we divide that for loop by the number of copies of the program that we have. So here is the initialization of our MPI world, it's called, so we can communicate with other copies of the program. The first thing we say is that we get our rank. That is our number in this system, and the number of total programs that are running. So I might be the 4th copy of this program out of 100 total copies. And that's important because that I know my own individual number, because that helps me divide up and figure out which rectangles under that curve am I responsible for calculating. So the for loop has been modified to take advantage of the fact that there are many programs now. We're going to divide up the work as evenly as we can, get just the sums for the rectangles that we're responsible for, or this copy of the program is responsible for, and then we are going to add up all of those copies, all of those rectangles to get a single value. The other thing we have to do is we have to broadcast to all the copies of the program how many rectangles to use. So the additional work is, one, knowing what my ID is and how many other copies of the program are running. Two, summing up my rectangles, the ones I'm responsible for. Then one of the copies of the program, and just one, sums up all of those rectangles that everybody else working on the problem sends to it. And we have to broadcast at the beginning of the program how many rectangles were there altogether. Doing all that, we can solve collaboratively the problem of calculating pi. All right, let's take a look at the corresponding Slurm script that will run this. Looks very familiar. It's really pretty simple. We have the same SBatch directives to the scheduler saying, in this case, we want 2 nodes. We want 4 copies of the program per node, and each is going to get 1 CPU, so we're going to have 8 total CPUs. So now we're actually allocating resources that a single program or a single set of programs are going to use with a single input. Now, remember, much earlier I said we have to make sure we have a mechanism for distributing our program across all the CPUs we're allocated. For the job arrays, that was fairly simple. We just ran a different Slurm script with 1 CPU, and it used up all the CPUs available. Here, we're going to use srun, and we're going to tell it to use MPI, and we're going to run it on a single MPI program with many instances, and we're going to solve that same billion rectangle problem we had before. All right, so that's our plan. We're going to have to install some Python libraries in order to use MPI. So that's our next step. For our MPI version of the Pi estimator to work, we're going to have to install MPI libraries. And we're going to use Conda for that again. Conda has a nice feature where you can actually install a list of packages somebody else created for you. So let's take a look at that. We have a directory here called conda-envs, and inside of there is mpi_numpy.yaml. And this is a list of the packages and their versions that I know work with this example. We're going to install that by saying conda env create. So for this, we need to add this env word. Then -- file, and then the name of the file that we're going to use to create our environment. So conda envs mpi numpy.yaml. And it goes out there and it starts downloading all of these packages. Now, the package we really care about is MPI released by Intel. That's the version we need to use. And we need to use this MPI for Pi wrappers so that Python can talk to the Intel version of MPI that we're going to be using. And this is handy if you want to, if you create a Conda environment you're really happy with and you want to distribute it to other people in your lab, you can just export it to a YAML file like this, give them that YAML file, and they can copy your environment exactly with this create -- file command. All right, so we've finished installing our environment, and we can activate it with conda activate MPI NumPy. I'd like to do a little interactive test just to make sure that everything's working as expected before we move on to a batch job. And we're going to use the debug partition for that. So the easiest way to do this is to just take a look at our batch script that has the command in it. All right. And we're just going to copy this line. Let's make it a little bit shorter. Let's do, I don't know, 1,000. We're going to run on the debug partition. And let's create 4 copies of our program, each of which will by default get 1 CPU. And so we should be solving this 1,000 rectangle problem using 4 CPUs at a time. There we go. It's allocated, it's running, it's already done. And that seems to have worked. So let's try submitting this with a much larger problem, because remember, we're going to compare this to our serial program, which had 1 billion rectangles. So we're going to batch submit this with 1 billion rectangles. We'll take a look at and see, is it efficiently using the CPUs? And we'll see how much faster did it actually solve the problem of estimating pi with 1 billion rectangles when you have, in this case, 8 CPUs, so 2 nodes, 4 CPUs per node, as opposed to the serial version. Is it really going to be 8 times faster? All right, so let's submit this. All right, looks like it's running on Hopper 11 and 12. All right, our job is finished. Let's take a look at the output. Your job IDs, of course, will be different than mine, but using 8 CPUs, it took about 9 seconds to calculate pi using 1 billion rectangles. Let's compare that to our previous serial version. That took about 80 seconds. So this is pretty close to perfect scale-up, where the ratio of time taken is pretty close to the number of CPUs we allocated to the problem. So, of course, these are all just examples. It might seem silly to try and reduce the time from 80 seconds to 9. But for many problems, we're talking about hours, days, weeks, months of compute time. And if we can divide that time by 8, in this case, by adding MPI, that is well worth it. So instead of taking 8 weeks, it's going to take 1 week. If we can parallelize this and the scaling works the same for 50 CPUs, then it's going to complete in 1/50th the time. And despite the learning curve of learning how to use Slurm, MPI, these other things, the payoff is really enormous. If you can do things 50 or 100 times faster consistently, you're going to be able to do that much more research. Thank you for watching this tutorial. As always, please reach out to me and the rest of the CARSI team through help@carsi.unm.edu if you have questions.